Welcome once again to our lessons at back. In the previous lesson, we looked at how the capacitance is increased by inserting a dielectric between the plates of the capacitor. We did experiments about that and we found that it is actually true. But how does it come about? How do we have a dielectric give us more capacitance? That's what we are going to handle in today's lesson. And therefore, our topic, we are going to handle the action of a dielectric. We shall look at the effective of certain capacitors arranged either in series and in parallel. Then we shall congratulate ourselves. So now let's look at action of a dielectric. Action of a dielectric. Actually, somebody can ask a question that explain why a dielectric is placed between the plates of a capacitor. If somebody asked you to explain why a dielectric is placed there, you may not simply say because it increases the capacitance of that capacitor, but you have to go a step further and back your reason why, how comes it increases the capacitance. So let's consider some capacitor. Let's say these are two plates of a capacitor, where this one is the positive plate and this one is the negative plate. So what happens? There is a field intensity. There is an electric field that is in that direction. So let us insert a capacitor in between them. When you insert, let's say we have inserted this material as a capacitor, what happens to the atoms within this material? Because this is the field is in this direction, it is going to displace the positive charges in the other direction and then the negative charges in this direction. What do I mean? Simply, there are several atoms that I just want to represent, maybe like that. Of course, they be very many, okay? They be very many, right? Very many atoms within this, okay? Now, what happens? Of course, within this has positive and negatives, positives, negatives, positives, negatives, positives, and negatives. So what happens is that the electrons will be dispersed in the side that is to the side of the positive plate. Okay? Then these ones on this other side, the positives on this other side. The same here, negative here, positive, negative here, positive here, negative here, positive here. You can see that this positive is a neighbor to this negative. Okay? So the same, negative, positive, negative, positive, negative, positive, negative, positive, negative, positive, negative, positive. So we shall have positives here. Okay? This far end, we shall have the positive, and this far end, we shall have the negatives. So let us see what exactly happens once these electrons are displaced sideways on this side, and these protons or these positive charges on this other side adjacent to this. What happens? These ones within this positive will neutralize this negative. This positive will neutralize this negative. This positive will neutralize these negatives. Actually, we call them dipoles. So, such dipoles within the bulk of the dielectric neutralize each other. But you realize, because this dielectric is not touching the plates, you realize that these ones, the bound charges are not neutralized. So what happens? Within our plate, which I can maybe say, this is how we have it. The remaining, we are remaining with, so this was positive, and then within now this dielectric, there are negatives here. This is negative, and then there are positives here. So what happens? What happens is that, remember, there is a field due to these charges on the plates, okay? Another field is going to be created, which is in the opposite direction, because a field moves from the positive to the negative. Therefore, we shall have another field. So this was the electric field. This is now electric field within the what? The dielectric. That means that the field intensity has reduced since this one is opposing that one. Meaning that the effective electric field will be the original one minus this one due to the charges that were formed within the electric. What does it mean? We studied that electric field intensity is equal to the potential gradient. In other words, electric field intensity is proportional to the electric potential. What does it mean? The electric field intensity has reduced. Okay? The intensity has reduced, meaning that potential will also reduce, because the potential is proportional to the field intensity. Okay? What is capacitance in terms of potential? Capacitance, by definition, the ratio of magnitude of charge toward to the potential difference. What does it give you? This gives you that capacitance is inversely proportional to the potential. And we are saying that reducing the field intensity has led to the reduction in the potential. And since capacitance is inversely proportional to the potential difference, and the potential difference has reduced, that means that capacitance has increased. You got a point? That's how the dielectric, when inserted between the plates of the capacitor, is able to have the capacitance increase. Why? Once the field intensity is there, these are displaced as shown in the diagram. The dipoles are actually formed, which creates a field intensity after the bulk charges, the bulk dipoles neutralize each other. We only remain with the bound ones, which will create a field intensity which is opposing the one that we had originally. That leads to a reduction in the effective intensity of the arrangement, which leads a reduction into the potential difference of the arrangement. And since potential difference is inversely proportional to capacitance, that one will lead to increase in the capacitance. You need to take a note. You only find this one at Baxter's equation for circuits, where we are saying that understanding is compulsory. You read, that is where you can find that. That's where you can find that. So our question was, explain why a dielectric is placed between capacitor plates. And I want you to draw this kind of a diagram. And when you draw I want you to show that if this is a positive plate of a capacitor and this is the negative plate of the capacitor, and then you insert a dielectric. If you insert that dielectric, then I want you to draw negative, positive, negative, positive, negative, positive, negative, positive. So that's what we have. And etc. They will be the same. I can only show the ones on the border. So negative, positive, negative, positive. At least you have understood that, and that is my aim. Okay. And etc, etc. So we have the field tested there. So this is of course the plus Q. This is the minus Q. Okay. And then of course after this diagram we shall have such representation of the diagram: positive, then negative, then our dielectric, negative, then positive. So on this one we are showing that there is a field intensity due to the dielectric. Okay, that there is a field intensity due to the dielectric, and this is the original field intensity. So you write, when a dielectric is placed between the plates of a charged capacitor, when a dielectric is placed between the plates of a charged capacitor, the electric field intensity E, due to the charges on the capacitor plates, the electric field intensity E due to the charges on the capacitor plates displaces the nuclei within the dielectric in its direction, displaces the nuclei within the dielectric in its direction, and electrons in the opposite direction, and electrons in the opposite direction. New line. This leads to the formation of dipoles. This leads to the formation of the dipoles. Full stop. Another new line. Within the bulk, within the bulk of a dielectric, the neighboring ends of the dielectric neutralize each other. The neighboring ends of the dielectric neutralize each other, leaving an excess of unneutralized charges, leaving an excess of unneutralized charges at the ends of a dielectric, at the end of a dielectric, whose sign is opposite, whose sign is opposite to that of the charges on the capacitor plates near them, whose sign is opposite to that of the charges on the capacitor plates near them. New line. An electric field of intensity ED An electric field of intensity ED is developed due to excess charges at its ends, which opposes the electric field of intensity E, due to charges on the capacitor plates. This leads to, that's a new line, this leads to a reduction in the intensity of the arrangement. I.e., the effective field intensity equals this one minus that. Full stop. Since E is proportional, since intensity is proportional to potential, the reduction in intensity leads to the reduction in the potential. That's the reduction in intensity leads to the reduction in the potential difference, PD, across the capacitor plates. And since capacitance is inversely proportional to the potential difference, a reduction in potential leads to an increase in capacitance. A reduction in potential difference leads to increase in the capacitance of the capacitor. Hence, inserting a dielectric between the plates of the capacitor leads to an increase in the capacitance. Only found at Back Science Education Consultants. Find us on our YouTube channel, BSc, Back Science Education Consultants, and subscribe and enjoy. Thank you for watching. Thank you for attending this lesson. May you be blessed. Be blessed.